Hello there, young students of chemistry. This is a very quick summary of the reading that I asked you to do in your textbook, starting on page 44, talking about the chemical laws. There are very few laws in chemistry, and some of atomic theory, which I would expect you to kind of get those models on your own. We'll go into more detail of modern atomic theory when we discuss quantum numbers. Law of conservation of mass. Really, Lavoisier was the initiator there. So law of conservation of mass says, mass is not created or destroyed. The real application for us is in balancing equations. Remember that when we balance equations, we are balancing equations with coefficients, and those coefficients are making the atoms on the left-hand side equal the atoms on the right-hand side. So atoms are conserved in chemical equations, but compounds are not. The law of definite composition and multiple proportions. I think your book called the law of definite composition the law of definite proportions. You'll see it in a couple of different ways. But basically what it's saying is that if you have a particular compound, the mass proportions of that compound are never going to change. If the compound is water, H2O, the mass proportions are always going to be a 2:16 ratio. And if the ratio is different, you are not dealing with a sample of water. So when that ratio changes, the properties of the compounds themselves change. And then, of course, the law of multiple proportions is basically saying when you have two different compounds containing the same elements, there's always going to be a whole number multiple of that mass combination. So here we can see that we have these two compounds of carbon dioxide. I think this is the same example your book used, where, if you've got 1 gram of carbon, the relationship here would be, in compound 1, there'd be 1.33 grams of oxygen with that 1 gram of carbon. But in the second compound, it has to be a whole number multiple, because if that 1.33 is a 1-to-1 ratio, that means that the mass of oxygen with the second compound in the carbon has to be a whole number multiple of that. And you can see that that ratio there is 2. So we have one compound that is 1 carbon to 2 oxygens by mass, and then our 1 gram of carbon to 1.33 grams of oxygen by mass, and then another one that has 1 gram of carbon to 2.66 grams of oxygen, which means that we have increased the number of oxygens by a whole number. That multiple is 2. We've doubled the mass of the oxygen that's in that compound, and therefore doubled the number of oxygens. So your historic models, please remember the Fab Four of atomic theory: Dalton, Thomson, Rutherford, and Bohr. Dalton was that first person who came along and talked about atoms at all. And Thomson, Rutherford, and Bohr. I love that Rutherford was actually Thomson's student, and that Rutherford set out to prove Thomson, his mentor, correct, and then proved him wrong. But so Dalton's model, basically he came up with some very important information about atoms, but had not a whole lot of evidence. He was right that atoms combine in simple whole number ratios, and he had some mathematics to prove it. He was right that atoms cannot change from one element to another. If we talk about nuclear chemistry there, it's getting a little dicey. But, he really only had his mathematical evidence of ratios there. And then came along discoveries of electrons and the charge of an electron and protons. And then after that, the discovery of neutrons in the atom. That came along way later. And the structure was really determined by 3 players, and that would be Thomson, Rutherford, and Bohr. Thomson had this plum pudding model. There's a great picture of it in your book on page 54, a representation of that model, where you'd have these positive goop with electrons kind of scattered through. And then Rutherford wanted to prove that with his gold foil experiment and said, uh-oh, there's something in there. There's something dense and hard in the center of this atom, and he discovered the nucleus. He knew that it was positively charged because the particles that he was shooting at the gold foil, those alpha particles were deflected. He knew it was dense because sometimes those alpha particles actually hit something and bounced back at him. And then Bohr's model of the atom is that orbital model where we have a nucleus with electrons orbiting the nucleus in a set path. You know, I'm thinking of, I think that character is Jimmy Proton, maybe. Jimmy Neutron, maybe? I don't know. But Bohr's model is that one with the nucleus and all those kind of circles that you see. It's a very common representation of an atom in chemistry. So just kind of get familiarized back with those models of the atom. Okay, subatomic particles. Please remember that you'll be expected to calculate protons, neutrons, and electrons with some isotope designations. The atomic number is equal to the number of protons, and this designation, that's the Z number down here. Sometimes, you know, you'll just see something Z10. Well, that means that's neon because that's the number of protons that are in neon. And then the atomic mass in this format is the number here. The mass is the total of the protons and the neutrons because those are the things in the atom that have mass. Electrons are so light, we just ignore their mass. And then for isotopes, the number that's going to change is this top number, right? Not the Z number. The Z number is constant for any given substance. And don't forget that we will put ion charges in as superscript format in the upper right-hand corner. This happens to be a cation of 3+, which means this isotope lost 3 electrons. Negative ions gain electrons, positive ions lose electrons. So looking at our periodic table, I chose a poor periodic table example to put up here, but these are our atomic numbers at the top, right? These are the numbers of protons. Typically the mass number is written down below on the periodic table, and that is the one that the College Board provides has the mass number at the bottom as well. And remember that that mass number is a weighted average. Like hydrogen has 3 different isotopes. The weighted average of all of the isotopes of hydrogen is 1.01. Hydrogen has lots of isotopes that weigh 2 grams per mole, some of them that weigh 3 grams per mole, but by far when we weight the abundance of that isotope in the universe, the one that's most abundant is the one that is closest to the 1 gram per mole weight. So remember that we can calculate protons, neutrons, and electrons using our AZ format. So for example, if we had a format that was a phosphorus, right? If we had this AZ format here, they're telling us that phosphorus has 15 protons, and the number of neutrons is 34 minus 15. Remember, that number might not be the same number that's on the periodic table because there are isotopes of different elements. So if we subtract there, 34 minus 15, I shouldn't have to do that in the calculator, 19 neutrons. And then notice that this is an ion, this is an anion. Anions have gained electrons. This gained 3 electrons. So in a neutral atom of phosphorus, the number of electrons would equal 15. But in this ion of phosphorus, the number of electrons equals 18. and we now call this phosphide because it is an ion. Okay, and then in your book, they also had some information about mass spectroscopy. I lost the page. And I love the way your book talks about this, which is why I wanted you to read it. However, I don't think that the data they're showing you is very clean. So this is all on starting on page 67. They also have a picture of the device. There's actually looks a little bit less phallic than mine because mine is in a different direction. They've got theirs bending somewhere else. But you can see that what happens is we have these elements and we heat them, we vaporize them, we heat them until they're vaporized. And then we ionize those atoms, and then we put them through an electric field and a magnetic field. That's going to cause those ions to bend. And depending on how they bend, we can see that we can have different ions. So we have this detector plate. When the ion hits it, it records that. We can see that the ions that bend the least. So if we come along this route on the inside, you would never see this if you looked at a mass spectrometer. I mean, this is all on the inner workings, but this one at the bottom is bending the least. And because it's least affected by the magnetic and electric fields, that means that it has more mass. We know that things that are more massive have more inertia. They're less likely to move. And the things that are lighter are going to bend more. So we have a greater angle here. So what they do is this data is measured in a percent occurrence. So we can see that according to this diagram, which is not very realistic, there are 1, 2, 3, 4, 5, 6 isotopes of this particular element. Because there are 6 areas on the detector plate that have lit up and said, hey, something hit me. And in order to determine the percentage, they would have data in that is showing up in percent occurrence. So on page 68 of your textbook, they're showing the intensity of those different masses, kind of in that middle picture there. They're showing a mass of 107 and 109 atomic mass units. And then they're showing, oh, there's almost 100% intensity on the 107 and just a little bit less on the 109. The data is not that clean. So this is what it really looks like. There's all this jumbled mess in here. This happens to be something that this was the only spectrometer data that I could find that I was allowed to kind of copy and paste here. But so you have all these little bumps in here, which, you know, typically we would ignore. We can see here that this is the most abundant isotope here at 40%. And then we have these others, right, at 10, maybe 12%. This should add up to 100, so we're missing something here. Some of the isotopes were not recorded if we add these at 10. So what they're showing is that every time there's a peak, that would represent an isotope. So while this data isn't good atomic data, it is what the data looks like. So we'd have 1, 2, 3, 4, 5 isotopes. And we would use that relative abundance to determine the weighted average of that isotope and therefore that mass that would go on the periodic table. So here's some data that's been cleaned up in a chart. Again, it would come from something that looks like this. And if we want the weighted average, what we're going to do is use the mass percent to get the weights for each of the different isotopes. So if this is 283.4 atomic mass units, we will take 34.6% of that number. So we are saying of the mass, 34.6% of that mass is coming from this isotope. So 283.4 times 0.346, 0. And then we would follow through with each of the other isotopes as well. 284.7, that's 21% abundance. We'll multiply that by 0.2120. And we would do the same thing for the third isotope, the heaviest isotope, and the most represented. So our weighted average should be closest to the isotope that is most abundant, because 44% of the weighted average is coming from that isotope. It's going to be close to this one too, because 44 and 34 aren't that very far apart. So 287.8, of course, times 0.4420, that gives us 127 atomic mass units there. We've got 4 significant digits. Let's keep the 0.2. And then 284.7 times 21.20, 60.36. And then 283.4 times 0.3460, 98.06. Add these together, and then we have the weighted average. $285.6. Oops. Atomic mass units. So because these two isotopes were relatively close to each other in abundance, we're looking at a weighted average that's right in between the two of them. I should have done something a little farther away, like hydrogen, where like 90% of the isotopes weigh a mass of 1. Okay, so that is how you calculate average atomic mass. This is what the inner workings of a spectrometer look like. This is what the data from a spectrometer looks like. And the College Board is really big on you getting information from data. So they might expect you to take a graph like this and read the mass, 7,700 and, I don't know, 70, and then multiply it by the 40, right? So they would expect you to read this down to get the weight, and then use the abundance here to multiply that by the percent. So that's kind of what you're looking at there. It's hard for me to find some examples like that, but I didn't feel like the data in your book, how they were representing the data, was good enough. It wasn't close enough to reality. Okay, that's all I need from you now.